Welcome to Elemental Science Magazine. From the quiet vantage point of space, our planet appears as a vibrant blue marble, swathed in the immense expanse of its oceans. It is a world defined by water, with this vital liquid covering more than 70% of its surface. This image, however, presents a profound and deceptive paradox. While we are surrounded by water, the vast majority of it, over 97%, is salt water, utterly undrinkable for humans and unsuitable for the crops that sustain us. The remaining sliver of freshwater is locked away in glaciers, ice caps, hidden deep underground, leaving a tiny, precious fraction available in our rivers and lakes. This fundamental scarcity has shaped human history, dictating where civilizations could flourish and where they could not. Today, this ancient challenge has reached a critical juncture, a confluence of powerful forces, a changing climate that disrupts predictable rainfall patterns, a global population that continues to expand, the relentless growth of our cities and industries is placing unprecedented strain on our finite freshwater supplies. Rivers that once ran strong are now shrinking. Ancient underground aquifers are being depleted faster than they can recharge. In this context, the immense, salty ocean begins to look less like a barrier and more like a lifeline. Desalination, the process of removing salt from seawater, is emerging from the realm of science fiction and becoming a fundamental tool for survival in the 21st century. This technology represents a monumental shift in our relationship with the planet. It offers the promise of a nearly limitless source of fresh water, independent of the whims of weather patterns and the constraints of geography. For coastal communities from California to Chennai, it presents a vision of water security, a way to sustain life and foster development even as traditional sources dwindle. Yet this promise is not without its complications. The process of wresting fresh water from the sea is an intricate dance of physics and chemistry, one that carries significant environmental costs and economic costs. It is a powerful solution, but it is not a simple one. As we stand on the cusp of what could be a global water revolution, we must approach desalination with both hope and caution. It is a technology that could indeed change everything, quenching the thirst of arid nations and securing the future of burgeoning megacities. But to harness its power responsibly, we must understand its workings, acknowledge its hidden costs, and strive to make its benefits available to all, not just the privileged few. The journey to unlock the ocean's potential is not merely a technical challenge, it is a moral one, forcing us to confront difficult questions about energy, waste. Every technological solution creates its own set of challenges, and desalination is no exception. While it masterfully produces life-giving fresh water, it also generates a significant and problematic byproduct, brine. Put simply, brine is the highly concentrated salt water left after fresh water is extracted. For every liter of fresh water a typical plant produces, it can generate 1.5 liters or more of super salty liquid. This brine is not just saltier than the ocean, it often contains a cocktail of chemicals used in desalination processes. For example, anti-fouling agents that keep delicate filters clean and functioning. The question of what to do with this massive volume of waste is one of the industry's biggest environmental hurdles. The most common, cheapest disposal method is to pump brine directly back into the sea. That may sound logical, returning salt to salt water, but it can have serious consequences for local marine ecosystems. Because brine is denser and saltier than surrounding seawater, it sinks towards the ocean floor, forming underwater plumes of hypersaline water. Many marine organisms are not adapted to such extremes: tiny plankton at the base of the food chain, delicate seagrasses, small fish that live among them. This can create localized dead zones on the seabed where biodiversity plummets and habitats degrade. The impact isn't limited to the discharge point. Over time, continuous release can alter the salinity and chemistry of entire bays and estuaries, especially where water circulation is limited. that can disrupt life cycles of commercially important fish and shellfish, harming local fishing industries. Discharge brine can also differ in temperature from ambient seawater, causing thermal pollution and added stress. Acknowledging and managing the brine problem is crucial for desalination's long-term sustainability. Ignoring it trades water scarcity for a different environmental crisis. The challenge is finding smarter, more ecologically sensitive ways to manage this waste stream. Regulators and environmental groups are pressuring the industry to move beyond simple ocean discharge. That pressure has spurred innovation to mitigate brine's harms. Engineers are designing sophisticated diffuser systems to mix brine more effectively with seawater, reducing concentration before it reaches the sea floor. And a more ambitious, sustainable vision is emerging, one that seeks to eliminate brine as a waste product altogether. The most forward-thinking solution to the brine dilemma is a concept known as zero liquid discharge, or ZLD. This is a paradigm-shifting approach that aims to transform the desalination process from a linear system, water in freshwater waste out, into a circular one. The most forward-thinking illustration of this is a closed-loop system, where brine is fed into a second facility that extracts minerals and water, with no liquid waste leaving the loop. The ultimate goal of ZLD is to eliminate the discharge of liquid waste entirely. Instead of viewing brine as a problem to be disposed of, this philosophy sees it as a raw material rich with valuable components. Achieving true ZLD is technically complex and often expensive, but it represents the pinnacle of sustainable desalination. It turns a significant environmental liability into a potential economic asset. The core principle of ZLD involves further treating the brine to extract every last drop of fresh water and then recovering the solid materials that remain. This is typically done through a series of advanced processes such as evaporators, crystallizers, which use heat pressure changes to separate the water from the dissolved salts. The result is a stream of very pure distilled water which can be added to the plant's output, and a solid cake of mixed salts. This solid waste is far easier and safer to handle and dispose of in a controlled landfill than a massive volume of liquid brine. It completely avoids the problem of creating hypersaline plumes in the ocean. While preventing marine pollution is a primary driver for ZLD, the economic incentives are also becoming increasingly powerful. The solid salts recovered from the brine are not just a uniform block of sodium chloride. Seawater is a complex chemical soup containing a wide array of minerals, some of which are highly valuable. Brine, being a concentrated form of seawater, contains these minerals in even higher quantities. Elements like magnesium, potassium, calcium, lithium, trace, uranium, trace. The workhorse technology behind most modern desalination plants is a process called reverse osmosis. While the name sounds complex, the underlying principle is remarkably elegant and can be understood through a simple analogy. Imagine a gatekeeper with an extremely strict entry policy standing before a very, very small gate. This gatekeeper will only allow water molecules to pass through, salt minerals, bacteria, viruses. In a real plant, this gatekeeper is a specially engineered membrane, a thin, semi-permeable polymer sheet filled with microscopic pores so tiny they are measured in nanometers. This is the magic at the heart of turning the sea into a source of life. In natural osmosis, water moves from less salty to more salty to balance concentration. Reverse osmosis does the exact opposite. Powerful pumps create immense pressure pushing seawater against the membrane surfaces. Pressure can be about 60 times atmospheric pressure. That pressure overcomes natural osmotic tendency. Small water molecules are forced through the tiny pores, leaving the larger salt and impurity molecules behind on the other side. What emerges is exceptionally pure, fresh water. Efficiency and durability of membranes are the keys. Membranes are typically wound into tight spiral cylinders, maximizing packed surface area in a pressure vessel. A single large plant can contain thousands of these membrane elements. But they are delicate and susceptible to clogging, fouling, biological growth, mineral scale suspended solids. Much of plant cost goes into pre-treating incoming seawater to remove these effluents and periodically cleaning membranes to keep them working at peak performance. The search for better, more resilient membranes drives innovation. Scientists are exploring new materials. One promising material is graphene, a single layer of carbon atoms in a honeycomb lattice. Graphene is incredibly strong. One of the most significant criticisms leveled against desalination has always been its immense appetite for energy. The process of reverse osmosis, pushing water through membranes at extremely high pressures, is inherently energy-intensive. Historically, desalination plants were often tethered to fossil fuel-powered grids, creating a troubling paradox. In solving water scarcity, we were contributing to climate change. The smokestacks of a power plant providing electricity to a desalination facility became a symbol of this difficult trade-off. This tight connection between energy consumption and water production is often referred to as the energy-water nexus. For desalination to be a truly sustainable, long-term solution, it must break its dependence on fossil fuels. The high energy demand does not have to equate to a high carbon footprint. The future of desalination is inextricably linked to the future of clean energy. The Middle East, North Africa, Australia, the American Southwest. This happy coincidence presents a perfect opportunity to power desalination with renewable energy, particularly solar power. The vision of green desalination is one where vast fields of solar panels or rows of wind turbines provide the clean, carbon-free electricity needed to turn seawater into fresh water. This synergy is already becoming a reality. A number of innovative projects around the world are co-locating large-scale solar farms directly alongside desalination plants. During the day, when the sun is shining brightest, the solar panels generate more than enough electricity to run the powerful pumps and systems of the plant. This dramatically reduces the facility's carbon footprint and can also lower the long-term cost of water production by insulating it from fossil fuel price volatility. Other renewable sources are also being explored, including wind power for coastal and offshore plants, and even geothermal energy in some locations. These hybrid systems are transforming desalination from a climate problem into a part of the climate solution. Furthermore, engineers are constantly developing new ways to make the desalination process itself more energy efficient. Section 7. Geopolitics of the Tapu, a tale of two realities. The ability to create fresh water from the sea is not just a technological feat, it is an act of immense geopolitical power. It reshapes a nation's vulnerabilities and opportunities, altering its relationship with its neighbors and its own landscape. However, this power is not yet evenly distributed. The high capital cost of building a large-scale desalination plant, which can run into the hundreds of millions or even billions of dollars, creates a stark dividing line between the world's haves and have-nots. This has given rise to two very different realities, a tale of two worlds when it comes to water security. Wealthy, technologically advanced nations, their lower-income counterparts on one side of this divide are countries like Israel, Saudi Arabia. These nations, facing extreme natural water scarcity, made strategic long-term decisions decades ago to invest heavily in desalination as a matter of national survival. Saudi Arabia, blessed with immense oil wealth, was able to finance the construction of some of the world's largest desalination facilities, using energy from its fossil fuel reserves to power them. This massive infrastructure program has allowed its cities to flourish in the desert and has secured its domestic water supply. It has turned the kingdom into a global leader in desalination technology and operations, a status it achieved through sheer financial might. Israel's story is one of technological prowess and state-led innovation. Lacking Saudi Arabia's oil wealth, hyper-efficient water management systems pioneering drip irrigation, mastering reverse osmosis technology. The country now gets a majority of its domestic water from the Mediterranean Sea, a feat that has effectively made it drought-proof. This water independence has not only boosted its economy. Section 8. The salt divide. A question of equity and access. The disparity in the ability to afford desalination technology is creating what can be called a salt divide. Fast cut. The ocean is a potential reservoir, but only for some. Price, finance, and capacity determine who benefits. This is a new dimension of global inequality. Access to the most basic human necessity, water, is increasingly determined by a nation's wealth and technological capacity. For countries that can afford it, the ocean becomes a reliable reservoir, securing their future. For those that cannot, the ocean remains an impassable barrier, a resource just out of reach. This divide is not just about running water. It affects a nation's ability to feed its people. It affects its ability to develop industries, and it affects the chance for a stable, healthy future for citizens. This inequity also plays out within countries. Even when a lower-income nation finances a desalination plant, often through international loans, questions of fairness immediately arise. Who gets the water? Is it piped to affluent urban neighborhoods and high-end tourist hotels, while poorer communities and rural villages continue to rely on contaminated wells or distant streams? The cost of desalinated water is almost always higher than water from traditional sources. If those costs are passed directly to consumers, the poorest households may be unable to afford it. The result? Water becomes a commodity accessible only to those who can pay. Addressing this salt divide requires a conscious and deliberate focus on equity. It is a call to think critically about how this powerful technology is deployed. It is not enough to simply build a plant. We must also build the policy frameworks to share its benefits. This includes exploring public-private partnerships that prioritize service to underserved communities, implementing tiered pricing structures where higher volume users pay more to subsidize low-income households, and investing in training of local workers to operate and maintain the facilities. International cooperation is essential, moving beyond loans to genuine technology transfer and capacity building. Ultimately, this is a profound ethical question. Is access to clean water a basic human right, or a service to be bought and sold? How we answer will shape the future of global water governance. If we allow the salt divide to widen, we risk a world split between the water-rich and the water-poor, with instability and human suffering. But if we view desalination through fairness and shared responsibility, we can create a more just and equitable world for all. We must ensure that the waves of innovation also lift the boats of the most vulnerable. Section 9. From waste to wealth. 2. The promise of brine, mining, and new membranes. The future of desalination will be defined by our ability to make it cheaper, more energy efficient, less harmful to the environment. A wave of innovation is sweeping the industry, promising to address its biggest challenges head-on. Two frontiers stand out. Next-generation membranes brine mining. Together, they could reshape the economics and the ecological footprint of turning seawater into fresh water, moving the process toward a circular, sustainable model. The goal is no longer just to produce water, but to do so with maximum efficiency and minimal waste. Leftover brine is a major environmental concern, but it's also a treasure trove of valuable minerals. Brine mining aims to unlock that value. Instead of discharge, concentrated brine becomes feedstock for a new kind of chemical plant. Using advanced electrochemical techniques, using advanced separation techniques, it becomes possible to selectively extract valuable elements. Lithium, present in seawater and concentrated in brine, is critical for batteries. Extracting lithium could provide a more sustainable source and reduce damaging traditional mining. But riches go far beyond lithium. Magnesium, used for lightweight alloys in aerospace and automotive. Potassium, recovered for agricultural fertilizers. Table salt, harvested for industrial use. Gypsum, harvested for industrial use. brine entering a system and being separated into pure water, table salt, magnesium, lithium, and other valuable minerals. Turning brine into multiple revenue streams can significantly offset operational costs. That economic incentive could drive adoption of zero liquid discharge systems, making environmental best practices profitable. Meanwhile, materials scientists race to create the next generation of reverse osmosis membranes. The goal: more permeable to water, more resistant to fouling, more effective at rejecting salt. That would let plants operate at lower pressures and lead to dramatic reductions in energy consumption. Researchers are exploring graphene carbon nanotubes, aquaporin-based biomimetic membranes, mimic how living cells transport water. Section 10, Conclusion: from paradox to purposeful action. We began with a paradox, a planet drenched in water where billions of people struggle for a clean, reliable drink. For centuries, the vast, salty ocean has stood as a symbol of this tantalizing but unreachable abundance. Today, technology is finally providing us with the key to unlock that resource. Desalination is no longer a futuristic dream. It is a present-day reality and a critical tool for navigating the water-stressed decades ahead. It offers the promise of drought-proof cities, resilient agricultural systems, and a new measure of security for coastal nations around the world. The ability to make the sea drinkable is, without a doubt, one of the most significant technological achievements of our time. However, as we have explored, this power comes with profound responsibilities. The brine dilemma teaches us that every solution can create new problems if not managed with foresight and care for the natural world. We cannot solve our water crisis by damaging the marine ecosystems that regulate our planet's climate and provide sustenance for millions. The high energy demand reminds us that our water security is inextricably linked to our energy choices and the urgent need to transition to a clean, renewable-powered future. The path forward must be one of green desalination, powered by the sun, powered by the wind, not by the fossil fuels that have pushed our climate to the brink. Most importantly, the salt divide serves as a crucial moral compass. The technology's high cost threatens to create a world of water apartheid, where wealthy nations secure their future, while poorer nations are left behind. We must actively work to dismantle this divide through international cooperation, technology transfer policies that prioritize equitable access for the most vulnerable. Small-scale modular systems powered by local renewables can bring water security to remote communities. Fair pricing structures can ensure that water remains a human right, not a luxury commodity. The purpose of this technology should be to uplift all of humanity. The future of desalination is bright, filled with the promise of more efficient membranes, the economic potential of brine mining, and the synergy of circular systems. But technology alone is not a panacea. It must be paired with a renewed commitment to conservation, fixing leaky infrastructure. Thanks for watching Elemental Science Magazine. Subscribe and hit like button if you want to learn more in science.